Solar thermal power, also known as concentrated solar power (CSP), is a technology that generates electricity by concentrating sunlight to produce high temperatures, which are then used to drive a thermal power cycle. Unlike photovoltaic (PV) solar panels, which directly convert sunlight into electricity, CSP leverages heat, making it an ideal solution for regions with high direct sunlight. Here's an in-depth analysis of solar thermal power, covering its various technologies, applications, economics, environmental impact, advantages, and challenges. There are 4 primary CSP technologies, each with unique design and operational principles. Curved, mirrored troughs focus sunlight onto a receiver tube containing a heat transfer fluid, often synthetic oil. This fluid is heated and then used to produce steam for electricity generation. This design is the most widely implemented and is commercially proven. Solar power towers systems use a large field of flat mirrors, or heliostats, to concentrate sunlight onto a central receiver at the top of a tower. The receiver contains a heat transfer fluid, typically molten salt, that absorbs and stores heat to produce steam. Power towers can achieve very high temperatures, improving thermal efficiency. Another system is linear Fresnel reflectors. Flat mirrors concentrate sunlight onto receiver tubes above them. Although they operate similarly to parabolic troughs, their simpler mirror design makes them more cost-effective. However, linear Fresnel systems have lower efficiency due to less precise sunlight concentration. Dish engine systems. Parabolic dishes focus sunlight onto a receiver at the focal point, where a Stirling engine or another heat engine converts heat to mechanical power, which is then converted to electricity. Dish systems are modular and highly efficient, but less commonly used for large-scale applications due to their high cost. 2. How solar thermal power works. Step-by-step process. 1. Sunlight collection and concentration. CSP systems use mirrors to focus sunlight onto a small area, creating very high temperatures. 2. Heat absorption. The concentrated sunlight heats a working fluid, such as molten salt, synthetic oil, or water, in the receiver. 3. Heat transfer and storage. The heated fluid can either be used immediately to produce steam or stored in large tanks for later use, providing power even when the sun is not shining. 4. Electricity generation. The hot fluid creates steam, which drives a turbine connected to a generator, converting thermal energy into electricity. 3. Energy storage in CSP. One of CSP's key advantages is the ability to store thermal energy, providing electricity after sunset. Common storage solutions include molten salt storage. CSP plants often use a mixture of sodium and potassium nitrate salts, which can be stored in insulated tanks for hours or even days, allowing power generation around the clock. This storage capability enhances grid stability by making solar power dispatchable. Phase change materials. PCMs absorb and release thermal energy during phase changes, that is melting and solidifying, offering high energy density and compact storage solutions. 4. Comparing solar thermal to other power sources. CSP holds unique advantages and challenges relative to other power sources. 5. Applications of CSP. Utility-scale power generation. CSP is best suited for large-scale power plants, making it a good fit for utility grids. Many large plants operate in sun-rich regions like the southwestern U.S., the Middle East, and North Africa. Industrial heating and desalination. CSP's high temperatures are beneficial in industries requiring process heat, e.g., chemical production, desalination of seawater. Thermal energy can also be used directly for processes instead of generating electricity. Hybrid power plants. CSP can be combined with other sources, such as natural gas or PV, to create hybrid plants that improve efficiency and reduce emissions. 6. Economics of CSP. Initial investment. CSP systems require a higher initial investment due to complex infrastructure and materials, mirrors, receivers, storage tanks. However, prices are falling as technology advances and larger plants achieve economies of scale. Levelized cost of energy (LCOE). As CSP systems become more efficient and storage costs decrease, the LCOE for CSP has become increasingly competitive with fossil fuels, especially in sun-abundant regions. Operational costs. CSP systems generally have lower operational costs than fossil fuel plants since they don't require fuel. Maintenance, however, is essential due to the precision of mirrors and tracking systems. Policy and incentives. Government policies, subsidies, and carbon pricing impact CSP's competitiveness. Many regions offer incentives for CSP to meet renewable targets. 7. Environmental impact. Land use. CSP plants require substantial land area, often in desert or semi-arid regions. While land use is high, environmental impacts can be mitigated by installing CSP on degraded or desert land with minimal ecological impact. Water use. CSP, particularly plants with steam cycles, can have high water requirements for cooling. However, dry cooling and hybrid cooling systems are now being adopted to reduce water usage. Greenhouse gas emissions. CSP emits no greenhouse gases during operation. Some emissions occur during manufacturing and construction, but these are significantly lower compared to fossil fuels. 8. Advantages of solar thermal power. Dispatchability. With thermal storage, CSP plants can supply electricity on demand, addressing a key challenge faced by other renewables. High efficiency. CSP plants can achieve higher efficiencies than PV due to the heat conversion process, especially at high temperatures. Scalability. CSP systems are ideal for large-scale installations, allowing them to generate significant amounts of power and benefit from economies of scale. Long operational life. CSP plants have long lifespans, often exceeding 30 years with proper maintenance. 9. Challenges and limitations. High initial cost. Despite decreasing costs, CSP is still more expensive than photovoltaic PV, partly due to infrastructure requirements and limited manufacturing scale. Geographic limitations. CSP is most effective in areas with direct sunlight, such as deserts, limiting its applicability in cloudy or high-latitude regions. Complexity. CSP plants require precise optics and tracking, which can complicate maintenance and increase operational costs. Water use. While solutions exist, cooling requirements can be an issue in water-scarce regions, where CSP plants might otherwise be ideal. 10. Future outlook. Advancements in materials, storage, and hybridization with other energy sources, PV or fossil fuels, are improving CSP's efficiency and cost-effectiveness. Emerging CSP technologies, like supercritical CO2 cycles, promise even higher efficiencies by operating at ultra-high temperatures, potentially making CSP more competitive with other forms of generation. As the demand for reliable, low-carbon energy sources grows, CSP has significant potential to complement PV and wind in achieving a stable, renewable-based energy grid. Its role will be most pronounced in sunny regions that prioritize sustainable, dispatchable power.